you one more example, and here we want to solve the initial value problem. We're given the differential equation, we're given the initial condition. One thing I just want to tell you that there can be a problem which can be solved by the separable variable, by homogeneous, and also by the exact. So all the methods are valid. We check the equation. Now we check this one. It's not separable. We are not able to separate it because 2 plus something is coming here. Then number 1, number 2, if we want to take this as homogeneous, no, it's not homogeneous because of this 2. These have degree 3, degree of 3, degree of degree 0. It's not. It means we have to check is it an exact differential equation. If we write in a differential form, we multiply by dx. So we get here x square, xy square into dx plus 2 plus x square y into dy is equal to 0. Now at standard form, we know that one is, this is my mxy dx and nxy standard differential equation. Differential form is this one. So we compare these two. So we can identify our mxy is equal to xy square and our nxy is equal to 2 plus x square y. Now we take derivative with respect to, which want to check is this exact differential equation or not. Partial m by partial y is equal to 2x, x is constant, and partial n by partial x is equal to 2 is 0, constant 0, we get derivative of 2x y. So this implies that partial m by partial y is equal to partial n by partial x, and this implies differential equation is exact. With the exact differential equation, then we can say, we can write here the equations that partial f by partial x is equal to mxy, and mxy is x y square, and we have partial m by partial f by partial y. We have partial f by partial y is equal to 2 plus x square y. So these are the equations, set of equation 1 and equation 2. This is my equation 1. That's my equation 2. We're going to solve this equation 1 and equation 2 to get the value of fxy. So as before, we say we always take this as the starting value. Start from here, and we just integrate it with respect to x. So I can write here what I'll get. I get here integral partial f by partial x into dx is equal to integral, we're having x y square into dx. And here we are just integrated partially. Y is constant. So the integral of this one is fxy is equal to integral of this one is x square by 2 y square plus we're having constant with respect to y. This is my equation E3. Now, as before, I take the value of partial f partial y from E3 and substitute in E2 to get the value of gy. So differentiating with this respect to y, so I will get here the values. Partial f is a function of x and y, so we write the partial derivative with respect to y. I get here 2 is considered 2, we get here x square y, and get here dg by dy. So this is my equation 4. So I, from equation 2 and equation 4, I put the value of partial f partial y here. This one, what I'll get? I get here x square y plus dg by dy is equal to 2 plus x square y. Now you can see it here very clearly that my x square y is cancelled with x square y, and I'm left with here the equation dg by dy is equal to, I can write here dg is equal to dy. I integrate this one, I get dg is equal to integral 2 into dy. I solve it, I get here gy is equal to 2y plus c1. I'm writing here the constant. Last time I have not written it, just to give you an alternate of that one. Now I substitute the value of this one E3, this is my E4. I put the value of the equation, the value of gy, here is E4, E5 and this is E3 and E3. I'll get here fxy is equal to x square y square by 2 plus gy. What's my gy? Is 2y plus c1 is equal to c2. So I take this c1 to the other side. I'll get here x square. I'll get here x square y square by 2 plus 2y is equal to c2 minus c1. I will write here x square y square by 2y is equal to c, where I write c is equal to c2 minus c1. We can do it like this one, or we can do as I did last time, that we just substitute the value of c at the end and we say this is equal to c. So this is my general solution. This is my general solution. Now my equation is, with the initial condition, I want to find the particular solution of the initial value problem. I'm given here the initial condition, that is y at x equal to 1 is equal to 2. So x equal to 1, y is equal to, I substitute in my equation here, in the solution, this is my E6. I substitute in E6. I'll get here this is equal to 1 into 4 over 2 plus 2 into 2 is equal to c. So my c is equal to 2 plus 4 is equal to 6. Substitute the value in E6. I get here x square y square by 2 plus 2y is equal to 6 is my particular solution. Particular solution, or we say solution of initial value problem. I say it solution of initial value problem. So this is the idea. I just give a quick revision of the details of the solution which we have done already. We are having here the differential equation and we are given here the initial condition. We have the differential equation and the initial condition. We call it as initial value problem, IVP. So we write our differential equation, compare with the standard form. I get the value of mxy, I get the value of nxy. Now we are having the exact solution to check partial m with respect to y and partial m with respect to x, because here is this dx, we differentiate with respect to y, and here we differentiate with respect to x partially. So partial m partial y, we get here 2xy, and partial m by partial x, this is 0, get 2xy. So partial m by partial y is equal to partial m partial x. That means differential equation is exact. If this is exact, then we can come here and we can write that this is equal to partial f by partial x and this is equal to partial f partial y, and then we use these two to find the solution as a function fxy. So we take the equation E2, E1, and we integrate this one partially with respect to x, and we integrate partially, y is constant, so get fxy, we get x square by 2 y square plus, here constant is g of y, because when differentiate with respect to x, this is partial of partial x, this will get here 2 is constant, xy square plus 0, this will be 0. Now, and now we want to find this one, we want to find actually gxy. So we have not used E2, we use E2, and then we use E2 and E3, and we will be able to solve it. Now we just take, we find the value of partial y here and substitute in this one. For partial y with respect to y, x is constant, is 2y, 2 is constant 2, and dg by dy. Now we are having here E2 and E4. I put the value of partial y here. So I get here x square y square dg by dy is equal to 2 plus x square y. So this x square y square x square y is cancelled. Always we have some cancellation at the end, and we get here simple form, and we get right here dg by dy equal to, again integrate it, we get here gy is equal to 2y. Here I'm just changing it from the last example. There I put the constant at the end, because first order differential equation will get only one arbitrary constant, but here I'm putting the constant just to teach you. So get 2y plus c. Now this gy I'm going to substitute here in this equation here. So I get here fxy is equal to x square y square plus 2y plus c1 equal to c2, because we are having here fxy, we say fxy is equal to constant. So we put here this equal to c2. Now simplify it, we take c1 to other side, say this is yet another constant, c is equal to c1 and c2. So this is my general solution of the differential equation. But I'm given here the initial value problem. We're given here y at 1, x equal to 1 is equal to 2. So we say when x is equal to 1, y is equal to 2. I substitute this value, x equal to 1, y equal to 2 in my equation. I get the value of y equal to c equal to 6. I put the value of c here. I get the solution. This is my particular solution. I say solution of the initial value problem.